as far as our introduction, what are we looking for? Again, what are we looking for? This is really a part of the entire campus. When we start talking about virtualization, we might be looking into the idea of VLANs. People have been using VLANs for a long time. Right? That's a layer 2 virtualization concept. Right? How do I keep the data away from my voice, essentially, that we're looking for? Lots of different reasons. How do I keep a group of A away from group B? And that allows us to have different broadcast domains in a layer 2 environment. The only way to get from one VLAN to another VLAN is through some layer 3 device, like a router. There is layer 3 virtualization that we have available for us. If you guys have ever dealt with things like virtual route forwarders that we have available for us, it allows us to be able to say, I want to keep company A away from company B, or even in groups of users. Here at Sunset Learning, we keep our classroom network away from our admin staff that we utilize. Right? But the idea is that they all use the exact same routers. I could go through and use access lists to say what you can get to and what you can't. Virtual route forwarders, or VRFs, allow for us to be able to say that there are 2 completely separate routing tables. As traffic comes in from the admin VRF, it can only be routed based off of the admin VRF's routing table. As it comes in from the classroom VRF, can only be routed based off of the classroom VRF routing table. We have virtualizations such as our services that we have available for us. Right? Virtualization in that case could be like virtual machines that we utilize. It could be cloud-based computing that we're utilizing. So lots of different architecture available for us when it comes to this idea of virtualization. Okay? Not just in one single spot. And some of the things we're looking for when we're going through and creating our design for our network, we're looking for scalability. How do we allow for the idea of growth of our network? Typically, when we judge for scalability, what we're looking for is to be able to assume a growth of 50% every single year. Okay? And how do we make sure that we've got that set up to be able to continue that growth from here on forward? Right? So when we start talking about scalability and that network design, it is before you even start to implement the network itself. We're looking for resiliency. We want to make sure things are always up and running. We've got redundancy. We're looking typically for no single point of failure in our network. This also means that we have to have things like proper dimensioning that we're utilizing, making sure that we have enough space or enough addresses for each user that's going to be a part of each individual location that's being there. When we look at redundancy, it might be redundant links. We're looking for redundant devices. We might be looking for the idea of redundant default gateways, redundant routes that we have available for us. So there are lots of different things that we're dealing with when we start talking about the idea of redundancy. And I also think when it comes to redundancy, think that there are really 2 separate things. There's redundancy and there's failover, okay? I think of failover as being something fails, we'll eventually be able to go through some other device. But it's not going to keep up things like a TCP connection, right? All those connections are going to drop and you're going to have to restart all those connections. Redundancy, something fails and we can keep those conversations up and running, right? So think telephone calls and TCP sessions that we've got available. That is really true redundancy that we're looking for. Obviously, any network that we're on has to support some type of security on the network, and that's based off of your risk assessment. Right? So what are we dealing with as far as my risk? What happens if someone should bring down our entire network? And then what type of security do we add to that to make sure that we're mitigating that risk if at all possible? Right? Obviously, security has to be right in line with what we've got as far as our risk assessment on that network. People like Sunset Learning obviously don't need to have the same type of security as, let's say, the NSA. Okay? So just to give you kind of an idea that there is definitely a give and take on what you use for security versus your mitigation of said security as well. Right? And then we also look for things like quality of service. I always think of quality of service as managed unfairness of bandwidth. The idea that we're trying to go through and say there's certain applications, there's certain things that we're sending across the network that are more important to the business than other things. Right? For instance, here at Sunset Learning, our video going to be much more important than things like email or general internet access up onto go see CNN or Fox News or whatever it is you guys want to go through and browse to, right? Because if my video doesn't work, I can't teach you guys. Right? That's what we do as a company. So that is our main goal in that case, is make sure that our video keeps on working at any given time. Right? So we have to go through and do an assessment within quality of service of what applications do we have, and what do we prioritize as a business within those applications as well. Being able to do things like, during times of congestion, I need to make sure my video gets X amount of bandwidth. I want to make sure that as it goes out of an interface, that we're sending really delay-sensitive conversations out before those non-delay sensitive conversations. My voice goes out, then my video goes out, then my mission-critical traffic, then my bulk traffic, and then maybe my best effort traffic after that. And when we start looking into network design, they deal with the idea of most of today's enterprise environments are built off of what they call a 3-layer hierarchy. There is an access layer, and the access layer is where you've got your users, your endpoints connected to that network. It's giving me access to the rest of the network that we have available to us. And usually at the access layer, this is where we're going through and doing things such as, might be my initial security. In quality of service, we might go through and police traffic on that network. I want you to be able to send HTTP traffic, but I shouldn't be getting 10 gigs of HTTP traffic from an individual user. I might go through and implement things like, how do I authenticate users at that point? Things like identity-based networking, or 802.1x goes through and allows us to say, before I enable the switch interface, give me your username and password so I can validate that you are indeed someone that should be on this network. We might be utilizing what we call a trust boundary for quality of service. Right? Do I trust distort code point or class of service markings that are coming in from these different devices? General rule of thumb is, if it's a phone, go ahead and trust those markings. If it's a PC, do not trust those markings. And we'll have to reclassify that traffic. Okay? And again, that's where you're going to typically do that classification. The hard classification in QoS is done here in the access layer. What we're going to do is think of things like access control lists that we use. We might use what they call network-based application recognition to recognize the type of traffic, and then we'll mark that traffic, or essentially color that traffic, if you will. The idea is marking, we can be done at both layer 2 and layer 3. I can set a type of service value in the layer 3 header, what they call a distort code point. I can set a class of service value in the layer 2 header. The idea is that as traffic comes in and I recognize this as voice, I want to mark that with a class of service of 5 and a distort code point of what we call expedite forwarding. Then all of the other devices, our distribution layer, our core layer, our routers, can then look at those distort code points or class of service values to determine what type of traffic that actually is. I don't have to do that same hard work of an access list on every single device to be able to recognize the type of traffic that it is. I can say, hey, I'm a layer 2 switch. I can look at the layer 2 header and recognize that's voice traffic, that's video traffic, that's mission critical traffic. At the distribution layer, typically where we're going to go through and enforce policy. And our policy is going to be things like our access list for who can send traffic to what subnets that are out there. So you're going to see a lot more of what we deal with as far as access control lists are available for us. It's typically our first spot where we start seeing routing involved. So a lot of times these distribution layer switches are running things like HSRP or VRRP so that we have a redundant default gateway for our users that are on our different VLANs. And then we have our core layer. And our core layer is essentially really only got one job. The idea is high-speed communication between the different distribution layers. Right? What Cisco likes to call the building block approach to campus design. Okay? Now, from there, they've gone more to kind of a concept, especially in the data center, you're seeing within here, where you're seeing what they call leaf and spine type of communication. Right? Now, this leaf and spine can be done in all sorts of different ways that we actually support within the data center. But a lot of times using what they call Cisco fast path switching, or TRIL, in the data center. Okay? The idea is that what we're doing is, rather than switching traffic looking based off of source and destination MAC address information, we're routing traffic through that link, okay, through those links. And if you think about the idea of routing, when you have multiple paths, equal cost paths in routing, we automatically load balance. When we have equal cost paths in switching, they say, yeah, spanning tree should shut down an interface. Right? So the idea is to be able to make sure that we don't really have to worry about spanning trees shutting down interfaces, and it allows for a lot of east-west bandwidth. I think a north-south bandwidth is from a user coming into the data center trying to get to the servers, and then the response from those servers back out onto those users. Okay? East-west bandwidth is from server to server type of communication that we're looking for. Right? The idea that we might be doing things like VMware, vMotion. I'm going to move a virtual machine from one physical server to another physical server with what they call migration of that. And I want to make sure that that virtual machine is always reachable even while it's in transport from one server to another server. Okay. So we're seeing a lot of the core distribution and access layer being a part of the enterprise campus, where we're seeing the spine and leaf being more of like the data center type of situations that we're looking for. So give you kind of an idea of what's going on within there. They show these issues are often found in poorly designed networks. We have large broadcast domains. Originally, when we started with networking, we used what we called a flat network. Everybody was a part of one big, huge subnet. And the problem with that is that that subnet is one single broadcast domain. One of these users sends out a broadcast and it interrupts absolutely everybody else's computer. And makes it very difficult to go through and implement security in that case as well, right? Because everything's being switched back and forth. You have to implement security from source to destination MAC addresses. So MAC addresses are used for our access lists, which become very difficult, especially when someone goes through and we get new laptops. We got to make changes to all of our security configuration that we have available for us. And then we also have failure domains. Perfect example right here, as a matter of fact. When we start looking at this, what happens if this one switch goes down? Basically, everybody is disconnected from the rest of the network. They lose access to our wireless LAN that we have, our wide area network that we have, our internet connection that we have. We can't even get traffic back and forth between these different locations anymore. Okay? So it becomes kind of a hodgepodge of what we have to do for security and what can we do for things like redundancy on that network as well. And so we mentioned that in most enterprise environments, we're looking for the idea of a hierarchical network. There's a three-tier model where we deal with the access, distribution, and core, each one having their own individual job to do on that network. There's a basic switch block, which they also sometimes call a collapsed core. Okay? In this case right here, think of there's only one building that we have available for us. So we have access layer switches that are in our closets, our wiring closets, as close as we can to our individual users. And then I connect all those different access layer switches through our distribution layer. Okay? The idea is that we don't need a core because we don't have multiple buildings to communicate back and forth between. And so in here, each one of these has their own individual job that we're dealing with. We mentioned the access layer has to deal with the idea of how do users get onto the network. Right? So we can do things like our trust boundary. We can do things like 802.1x authentication to validate who is that user. We have our distribution layer. And our distribution layer, typically what they call an L2, they're doing layer 2 switching between the access layer and the distribution layer, and then layer 3 across the core. Okay? So we're routing to get from distribution layer to distribution layer, and essentially from building to building that we look for. An L2, L3, L2 design. Okay? It goes from layer 2 switching to routing, then back to layer 2 switching in another building that we would have available for us. Okay? And then it allows us to connect our data center to the core. And the idea would then be, it doesn't matter where you're at in the rest of the network, essentially that data center becomes equidistant from all the different users in any given building that we have on that network in a campus type of environment. Again, they go through some of the other jobs that the access layer has to deal with. We said we need to enable end devices to connect to the network. So we're just simply looking for things like port density. How many users can I connect to that access layer switch? Right? Now, obviously, we've only got so many ports on the switch, so you might have to deal with the idea that even in the same wiring closet, we have multiple switches. Or those switches might be then combined together in what we consider things like a stack-wise capability, stacking multiple switches at the access layer. They show They're giving us network access control, so I can go through and determine who the users, what the device actually is, and what can those users get to on that network. We're looking for redundant uplinks. In this case right here, they're talking about redundant uplinks up onto the distribution layer. So if one link should fail, I've got another path up onto the rest of the network. It also gives us device redundancy. If one of our distribution layer switches goes down, I've got another path out onto the rest of the network. Typically, our access layer would be considered to be the idea of a field replaceable unit. If this switch fails right here, I've got to go through and replace it. I've got another one. All I need to do is just change all my ports, plug it into the new switch, put on a configuration, and let's go. Okay. Like this show, at the access layer, this could be layer 2, which you see a lot of originally. Layer 2 meaning that they've got VLANs for the different users to separate the VLANs. But this device that we're dealing with, this switch right here, is a layer 2 only device. It has no routing capabilities. So it's got to be sent up onto the routers. And in this case, the router would be our distribution layer. Our distribution layer being the default gateway for all those users on that layer 2 switch. Newer networks now support the idea of having these being layer 3 switches at the access layer. This guy right here is a layer 3 switch. So it is the default gateway for our users. The ability that, in that case, is now these links that go out towards the distribution layer are routed links. And it reduces the impact of what happens with spanning tree on that network. Right? We're trying to limit spanning tree from shutting down an interface. In a layer 3 environment, spanning tree is not used. Right? We're not dealing with the idea of saying they're redundant links in this switch topology. Now they're routed links, and we can automatically load balance on those links. People use a layer 2 environment when layer 3 switches were really expensive. Okay? Layer 3 switches are getting less and less expensive, so the idea is you're seeing a lot more people having that layer 3 at the access layer, so you're minimizing where you're seeing spanning tree on the network. Okay? What we call our spanning tree domain. We mentioned our distribution layer. Distribution layer is used for a couple different things. It interconnects all the access layer switches, so when you have users that are connected to different switches in the campus environment, I'm using that distribution layer to get from access layer switch to access layer switch. I'm doing things like routing and packet manipulation, things access lists that we have for security on that network, quality of service so that we can put it in the correct queue and send it out at a specific time, giving it a specific amount of bandwidth on the links out on towards the core. We're also trying to be able to support the idea of redundancy. So typically you see multiple distribution layer switches that we use. And it adds to our scalability on our network as well. Our core layer, we mentioned, really has one main job: high-speed forwarding between the different distribution layer switches. Okay? We're looking for it to be always available service. Now, this being said, you're typically not going to see a whole lot of policies in the core, access lists and things like that. We're going to do that at the distribution layer. Not to say that you won't see any access lists. If we see an access list in the core, it's typically a pretty simple policy. Right? And the idea is that most of our data is going to be permitted through that link. Okay? If I'm going to block data, I'm going to be blocking that at the distribution layer. Now, you can kind of determine whether or not you need a core device. Without core devices, what we have is, they call it a collapsed core. Okay? So let's say in this case right here, we got just 2 different buildings. I'm going to say we have building, they show building 2 and 4 to begin with. Okay, let's just say that we have those 2 buildings. And what we need with it, without a core device, is we need every distribution layer switch to be connected to every other distribution layer switch. So I've got a connection to the distribution layer switch inside the same building. And I've got a connection to each one of the 2 distribution layer switches at the other building. Likewise, this guy out over here has 2 links back and forth, and these guys have a link in between the 2 in a full mesh environment. But think about what has to happen when you go through and add in another building. I put in my 3rd building on this campus. It's got their own distribution layer switches. And we're going to have not only the link in between the 2, but now we're going to have a 1, 2, 3, 4, 5, 6, 7, 8 different links between these different switches. And think of where we have to make those changes as well. I have to go into all 3 buildings and make changes to both the distribution layer switches and all those buildings. When you go through and add in another building out over here, again, these guys will be connected directly between each other, and then they've got to add in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 different links to be able to support that. Okay? And again, I have to make changes to every single building block in this case. Whenever you look at a full mesh environment like this, it never scales well. Right? You can think of full mesh as being how many links you need in the middle. It is n times n minus 1 divided by 2. N being, in this case, the number of distribution layer switches that you have. Let me give you an example. With 79 different distribution layer switches, you have over 500,000 interconnects between those guys. Okay? So it just doesn't become scalable. I mean, give me a switch that has over 500,000 connections on it. You don't see them much, okay? Unless it's some type of service provider type of switch that we're looking for. So when we start getting to multiple building blocks, usually you start to see people looking for a core. And the idea of the core is it basically changes this full mesh between the different distribution layer switches into a dual hub and spoke design. Now notice we have 2 core layer switches here in the middle. And what we got is that each distribution layer, they have a connection for each core layer switch. When I add in a new building block, here's my new building block that we're adding, I add in 1, 2, 3, 4 different links. And if you take a look at where we had to go through and configure that, I need to touch the core and the new building. Okay? I add in another new building out over here. I add in 1, 2, 3, 4 different links. Okay? And again, make a change to the new building and the core layer switches. I never had to make a change to the other 2 buildings that we have to deal with at this point. I add in my 4th building, and again, it's 1, 2, 3, 4 different links. And again, making changes just to the distribution layer at the new building and in the core layer switches. So essentially what we've got now is we've got a dual hub and spoke type of environment through that core. It adds to redundancy, the idea that we've got 2 different paths within here. Not only do we have device redundancy in each building, but there's device redundancy in the core, and then there's link redundancy everywhere as well. Dramatically reducing the number of links we need to connect all of these different building blocks together. A spine and leaf type of situation typically used in things like Trill, okay? Or you can also think of things like Cisco fabric path switching on your Nexus devices, utilizes this concept of a spine and leaf type of topology. When you guys go into and start playing around with things like a DNA center is going to go through and utilize this concept of spine and leaf topologies. And the idea within here is that typically we're taking layer 2 services, things that are normally switched based off a source and destination MAC address, and we're putting that on top of a network that is all routed through the network. Okay? Fabric path is used by taking an Ethernet frame and encapsulating that with a fabric path header, which tells you to get from source to destination leaf node switch. Right? And it's physically routed through this environment at this point. And you'll see, this allows me to go through and say, I've got extra bandwidth as it goes from one leaf to another leaf. Multiple paths can take place to get from a host that's sitting out over here to a host that's sitting out over here. I've got paths that I can go in this direction through this spine. I can go through this spine. I can go through this spine. And I can go through this spine out over here. And because these are all routed links within here, they're automatically load balanced based off of our routing protocol, which allows us to say when we need more bandwidth, we can do a couple different things. I can add in a new link between these leaf and spines. Okay? Added another link out over here. And if I do that for each one of these guys, now I have 8 paths back and forth between the 2. I can also go through and say, hey, if I want to, we can add in a whole new spine as well. and have all of these guys multiply connected to each one of our spines, and have just, again, more links that we use for load balancing of that traffic across that link. Right? We don't have to make changes to an ether channel bundle. We don't have to go through and bundle anything, as a matter of fact. These are just separate links between the two switches that are seen as then routed interfaces that are being used. Gives me a lot of east-west bandwidth in things like a data center, if you will. So we said, in most of our network, we're going to be utilizing that 3-tiered environment, where in the data center, you typically see the things like that 2-tiered environment. Now, you might see in some branch offices or some remote offices that we don't need a core because it's not a part of a quote-unquote campus, right? There are only a certain number of access layer switches, so we only need 2 distribution layer switches in that case. And to get to everything else, it's got to be routed through some type of WAN connection that we utilize. Could be an MPLS or Metro Ethernet, or even via regular internet access via things like a VPN that we're utilizing, an IPsec VPN tunnel. Now, they also discuss the idea of cloud computing in this case. And whenever you start talking about cloud computing, the idea is that you've got data that can be reachable, that is not necessarily a part of any one given network for my company, okay? Now, this could be the company-owned cloud that we're utilizing. They typically have that at some kind of a co-location type of environment that we're going to run our own cloud for. The idea being is that if we lose connectivity to the corporate headquarters, users in other branch offices or from home, they can still reach those resources available for us, okay? Now, this could also be not a private cloud, but a public cloud that we utilize. And any of you guys using things like Microsoft Office 365 cloud services, Amazon Web Services, or cloud services that we can use. We keep data out on that network. They ship computing is delivered as a service rather than a product that we have to buy and maintain as well. Okay? And again, they show when we start dealing with this, there are different types of clouds. There are private cloud. It's owned by a single organization. There are public cloud. They're deployed by a provider for public use. Okay? We start looking at things like we mentioned, the idea of Microsoft Office 365 would be a public cloud that's being used. There are community clouds. They're shared by several organizations, but the idea is that we're keeping organization A away from organization B. If you guys have ever used things like Salesforce, a perfect example of a community cloud. They're all run on the same servers, essentially, but the idea is that Salesforce is keeping company A away from company B. Okay? And you might potentially have the idea of 2 or more clouds. I got a private cloud, a public cloud, and a community cloud. Right? We might see that here at Sunset Learning, as a matter of fact. Okay? Some of the things that we could potentially do within here. And when we look at cloud computing, you will see they have infrastructure as a service. Okay? Just give you kind of an idea on the test, they will call it oops, let me write it in a different, I can't see very well. AAS, infrastructure as a service. Okay? And the idea in this case right here is that the service provider deals with these bottom 3 things. They're going to deal with the physical devices for networking. They're going to deal with what do we need for storage space, what hard drive space are we going to use, and where are we going to keep that data. Right? They're going to have the physical servers themselves. And they're going to set up typically some type of virtualization so that as a company, I can create on that server a virtual machine. The customer then is in charge of going through and saying, all right, now that we got our virtual machine, what operating system do we want to run on that virtual machine? What kind of middleware software are we going to run on that? Right? When's it going to be up and running and available for us? What kind of data and applications are we going to save on that device? Okay? So the idea is that we're looking for the concept of being the CPU, the disk drives, the networks, the data center, that's all managed by the provider. But what runs on that is managed by the customer. Then there is platform as a service. Okay? And now what you're seeing is that the service provider is really in charge of not only all the physical devices, but also the virtual machines. They're going to configure the virtual machines for you. What you're going to do is you're going to say, what kind of data are we going to have on that virtual machine? What applications is that virtual machine going to run that we can access as a company? This allows for us to allow the service provider to go through and say, hey, when there's a problem with, say, VMware, it's their job of going through, that's a part of the virtualization, so it's their job of going through and upgrading VMware and keeping that up to date as far as any kind of licensing might be involved. Right? For the operating system, if you need to go from Windows 7 to Windows 10 or whatever it is that you're utilizing as far as the servers are concerned, right? They're the ones that are in charge of upgrading that operating system. All we're really doing as a company now is saying what kind of data and applications are going to be stored on that device. Okay? And then last but not least, we have what they call software as a service, or SaaS. Essentially what you're looking for is now the service provider in charge of everything. All we do is use that as an application. You think about that, like I mentioned the idea of things like Microsoft Office 365, okay? They've decided absolutely everything how it's going to run right down to the individual application. All we're doing is just using that application to be able to send traffic, like email, whatever it may be. Now, when we start talking about this device architecture, you're going to see that we have a data plane. The data plane is the networking device. Now, originally, before all of this virtualization happened, that device was not only in charge of switching or routing traffic from one interface to another interface, it actually ran the control plane. So this is where you're learning routes via our routing protocols, building a routing table, and determine how to route that traffic from one location to another location. And it had the management plane on it. Like we went through and configured each device one at a time. The idea being is that there's some types of traffic. We mentioned things like exception traffic, traffic that is dealing with, I need to telnet or SSH into the router. That has to come in on an interface, be sent up to the CPU and processed by the CPU and software, and then sent back out to that same user. There's then also the traffic that transits that router or switch, okay? That's typically going through just the data plane. So as traffic comes in on an individual interface, we can look at hardware ASICs to find out how do we route that traffic and what outgoing interfaces are going to go outbound on. How do I do layer 2 rewrite information and send it out the correct interface that it needs to go through. Okay? It allows us to then switch or route that traffic in hardware versus software. Much faster kind of communication that we have available for us. Now, once we start looking into the idea of software-defined networking, the whole idea is that we are changing the data plane, the control plane, and the management plane that we've got. They're taking it away from the physical devices. Now my physical devices that we're utilizing, our routers, our switches on the network that we have, those are all just simply going through and dealing with transit traffic. On my control plane is via our SDN software. Right? Cisco uses DNA Center for this. Right? The idea is that I go through and make my changes in DNA Center, and it pushes those changes down to these routers and switches that are out over here in their hardware cache that we're looking for. In our control plane, it runs the routing protocols to determine what is the best path from one location to another location. Okay? It's doing things like traffic engineering and mobility of our users as they move across this network. And then we have northbound APIs to be able to communicate with other applications. Think for data center, I might need, or DNA center, we might need to be able to communicate with things like an ICE server. Cisco's Identity Services Engine is what ICE stands for. Allowing us to be able to have usernames and passwords, authenticate our different users that are out there. ICE can also go through and say, not only is that a valid user, but here's what VLAN they should be a part of. Right? What they can get to, all sorts of different things. What security device group are they going to be a part of? So there's all sorts of different things that can be tied in with DNA Center and ICE. And again, when we say virtualization, virtualization is a loaded gun because it can be a lot of different things. There's virtualization in your switch software. Like I said, VLAN's been around for a long time. There's virtualization in your routing that we have available for us within VRFs. Virtual route forwarders that we can use. There's virtualization in the physical server as well. Here they're talking about the idea of using things like VMware. Okay? It's a perfect example of what we use. In a traditional networking environment, what we would have is that, let's say what we've got is I've got an email server, I've got a database server, and I've got a web server that we're dealing with. Okay. Notice our email server, they're showing it's a Windows device. So assume it was things like Exchange that we had running on that server. It was its own physical server with its own operating system that we had available for Windows. And on Windows, we had the application of Exchange to be able to go through and do email back and forth between the two. And even though that device had to be up and running all the time, we need to make sure our email is always available. We typically, as far as an average load of most email servers, you're not going to see email constantly coming through all the time or constantly going out. So typically our average load is only around 20% of that email server at that point. Right? But the whole concept was I had to keep the device up and running 100% of the time. So 100% of the time, it's consuming power. 100% of the time, it's generating heat. 100% of the time, because it's generating heat, I got to cool off the data center more. And it also takes up more and more space. The more devices that we need to support, the more space in the data center. So our data centers got bigger and bigger and bigger. Again, we get to see our database server that we have. Average load's only around 10%. Our web server, average load only around 40%. So even though all these devices were constantly on, they're not used 100% of the time. Right? So we're seeing less value of that physical hardware. Okay? When we went to the idea of virtual machines, the concept is the hardware itself, one single server that we have available for us, and it has a hypervisor, VMware, that we're utilizing. Okay? VMware is essentially the concept of being able to connect the virtual machine to the physical hardware that we have. And how do they send traffic to the CPU? How do they send traffic up onto the network interface cards? How do they use memory on that network? And then on top of that hypervisor engine, they allow us to have a virtual server. And our virtual server has virtual hardware, like a VNIC that we have available for us. They have their own operating system. They call it a guest operating system that runs applications. And now we can put multiple virtual machines on the same physical server that we've got. With all these virtual machines, they add up to around 70% utilization. Right? So not only is it on just one single device, so it takes up less room, less heat that we're going to see, so there's less cooling that we have in the data center that we have available for us. But now we're also seeing more of a utilization of that device as well. And they show it's that hypervisor that goes through and is controlling how the guest operating system connects to the physical hardware in the device. Right? So we're going to create a virtual network interface card for the virtual machine, and we're going to connect that VNIC to a physical network interface card that we've got on the physical hardware of the server itself. How do they communicate with the CPU? I can go through and say, hey, this is more important than this application that we have. So they give this more time on the CPU than the other device that we have available for us. I can allocate based off the amount of memory that the physical server we have, how much is dedicated to each one of these virtual machines. And you'll see there are a couple different types of virtualization. We have what they would call type 1 type of virtualization that we see. Not only do we have a hypervisor that controls how we communicate with the physical hardware, but each one of our virtual machines has their own guest operating system. Okay? Now notice in this case, there is no physical operating system on the device. What they would call a host operating system. At the type 2, now they have a host operating system that is underlying that. So you see this used quite often when you start dealing with things like go from VMware to things like VMbox by Oracle. Okay, so they run a Linux operating system, and on top of that, then they have their hypervisor for VMbox to be able to support the different guest virtual machines that we're utilizing. And they show these VMs have what they call a virtual network interface card, and they're connected essentially to a virtual switch in VMware. And that virtual switch then connects them to the physical interfaces that we have on the physical switch itself, or the physical server itself. So that allows these virtual machines to be able to communicate with each other back and forth through that virtual switch and out onto the wired network as well. Now, we also see that they have containers versus virtual machines. A virtual machine has its own guest operating system, okay? So we're actually running Linux or Windows or whatever you might want to use for your guest operating system inside the virtual machine versus a container. The containers have no guest operating system. What they utilize is the underlying host operating system that we have on that device. Now, why do they bring this up? Well, now if you start looking into things like the 9000 series Catalyst switches, they support on the switch itself both VMs and containers that can be used on that switch. Right? So we could do things like one of these could be a database, like MySQL that we're utilizing. One of them could be things like an application. Think of things like a print server. I see a lot of people running on those devices. Right? So I don't have to have an external print server. I can do that right there on the local switch. We can virtualize our network that we're dealing with within a routing environment. We mentioned, and the switching environment. In layer 2, we've had VLANs for a long time. Okay? And it keeps traffic separate from each other, essentially creating different broadcast domains. Each broadcast domain is its own logical subnet. And to get from one subnet to another subnet, you had to go through a layer 3 device. We also now have layer 3 virtualization. Layer 3 virtualization uses what they call virtual route forwarders, or VRFs. You might have heard some people call them a VRF, okay? Just to let you guys know. I usually just call it a VRF. But the idea is that what we've got is I've got interfaces that are associated with a VRF. That VRF has a routing table and potentially even a routing protocol on how we learn how to get to other interfaces that are part of that same VRF. And as traffic comes in on an interface associated to this dark blue VRF, I can only route that based off the VRF's routing table and what interface it can go outbound on. And this allows me to keep in Sunset Learning, I keep my classroom network completely separate from my admin network. They never learn how to get back and forth between the two, so I don't have to worry about things like access lists and what kind of traffic can go back and forth. That's kind of what they're looking for as far as virtualization and networking, and the new kind of main thing of what we're dealing with as far as a virtualized network in today's day and age. Okay, we're seeing more and more virtualization, and more of that really means that it becomes more and more complicated. Right? Essentially, what you'll see when we start dealing with things like DNA Center. DNA Center uses the global VRF as what they call an underlay network. How do you route from device to device to device to device? And then we create overlay networks, which are these other VRFs that we're looking for, and not a VLAN, but what they call a VXLAN that can be routed through an environment to go through and be able to connect different users together on that network. Okay. So lots of good things coming out when we start talking about virtualization in today's day and age. So do we have any other questions? Or any questions, I guess, since no one's asked one yet? All right, well, if there are no questions, that's kind of what I've got for you for this hour. Well, thanks for coming. Have a nice week.